Welcome back. So in the last section of the course, we talked about this situation where the response was quantitative or regression. In this section, we're going to talk about classification, where the response variable's got two or more values. And this is actually a very commonly occurring problem, actually probably more commonly occurring than regression. In machine learning especially, there's a big concentration on classification, where, for example, we're trying to predict whether an email is good email or spam, or in a medical area, we're trying to predict whether a patient's going to survive or die with a given disease. So it's a very commonly occurring problem and very important. So we're going to spend some time today on this, actually in the next set of lectures on classification. And Trevor and I are both here. Trevor's going to give the most of the talk, and I'm going to pipe in and correct him when he makes mistakes and make fun of his accent and things like that.
That means we won't hear much from you.
We'll see.
Anyway, let's go to the slides. The first thing we do is just show you what categorical variables look like. I'm sure you know. So for example, eye color. That takes on three values, brown, blue, and green. Those are discrete values. There's no ordering. They're just three different values. Email, we've talked about already, is spam and ham. I like that word, ham.
I like ham, I think.
Okay. I wish I'd thought of it. Anyway, ham is good email. So spam filters need to classify into spam or ham. So what is a classifier? Well, you've got a feature vector x, just like we had in regression, and now you have one of these qualitative response variables, like those above. And here's the mathy description of a classifier. The response takes values in a set C, which is a set of discrete values, and the classification task is to build a function, takes x as input, and delivers one of the elements of the set C. And so this is how we write it in math language. C of x gives you values in the set C. So for example, in the spam ham problem, C of x would either come back as spam or ham. Now, although classification problems are always couched in this form, we're often more interested in estimating the probabilities that x belongs to each category C. So for example, it's more valuable for an insurance company to have an estimate of the probability that an insurance claim is fraudulent than a classification fraudulent or not. I mean, you can imagine in the one situation you might have a probability of say 0.9 that the claim is fraudulent, and in another case it might be 0.98. Now in both cases, those might both be above the threshold of raising a flag that this is a fraudulent insurance claim. But if you're going to look into the claim and you're going to spend some hours investigating it, you probably go for the 0.98 first before the 0.9. So estimating the probabilities is also key. Okay, so here's some data. Two variables. This is the credit card default data set that we're going to use in this section. And the plot on the left here is a scatter plot of balance against income. So those are two of the variables. And as we can with classification problems, we can code the response variable into the plot as a color. And so here we have the blue points and the brown points. And the brown points are going to be those that defaulted, and the blue points are those that did not. Now this is a fictitious data set. You typically don't expect to see that many defaulters, but we'll talk about balance in classification tasks a little bit later as well. So in this plot, it looks like balance is the important variable. Notice that there's a big separation between the blues and the browns, the defaulters and those that didn't. Okay. Whereas with income, there doesn't seem to be much separation at all. Okay. In the right, we actually show box plots of these two variables. And so we see, for example, for default, there's, I beg your pardon. Default is at the bottom, no or yes in both cases. We've got balance, and we've got balance, and we've got income. And here we also clearly see that there's a big difference in the distributions, balance and income. Sorry, I beg your pardon, balance, default or not, whereas for income, there hardly seems to be any difference.
I've never seen a box plot before. What is that?
Oh, you tell me, Rob.
Okay. Well, see, a box plot, what's indicated there, Trevor, you can point, the black line is the median.
There's a black line, that's a median.
So that's the median for the yes, for the people, the median income for people who have defaulted. And then the top of the box, where are the quartiles? That's the 75th quartile, 75th percentile quartile, and the 25th is the bottom of the box.
So really a good summary of the distribution of income for those in category yes. What about these things at the end, Rob?
Okay, I think they're called hinges.
And they are called hinges.
And those are the ranges, are they, or approximately the ranges of the data?
Yeah, I think a hinge is defined to be a fraction of the interquartile range. And so it gives you an idea of the spread of the data.
Right.
And if data points fall outside the hinges, they're considered to be outliers.
By the way, it's a very useful data display. Almost one of the first things you should do when you get some data to analyze is do some scatter plots and create some box plots.
Who invented the box plot, Don?
John Tukey.
John Tukey, one of the most famous statisticians. He's no longer with us, but he's left a big legacy behind. Okay, well, one question we can ask is, can we use linear regression to solve classification problems? It seems like we may be able to. So suppose for the default classification task that we code the response 0 if no default, 1 if yes default. Right? It's somewhat arbitrary, but 0 and 1 seems sufficient. And then we could simply perform a linear regression of y on x, with x being the two predictors in this case, and classify as yes if y hat's bigger than 0.5, 50%. Right? I mean, 0.5 is halfway between 0 and 1. It seems like a reasonable idea. Turns out that you actually can do this. For a binary outcome, linear regression does a pretty good job and is equivalent to linear discriminant analysis. And that's something we're going to discuss later. So for a two-class classification problem like this, it doesn't do a bad job at all. And there's even some theoretical justification. In the population, remember in the population, we think of regression as estimating the conditional mean of y given x. Well, in our coding here of 0 and 1, the conditional mean of the 0, 1 variable given x is simply the probability that y is 1 given x, just by simple probability theory. So for that reason, you might think that regression is perfect for this task. What we're going to see, however, is that linear regression might actually produce probabilities that could be less than 0 or even bigger than 1. And for this reason, we're going to introduce you to logistic regression, which is more appropriate. And here's a little picture that illustrates it. Here we've got our balance variable. Now we've plotted against balance, we've plotted the zeros at the bottom as little dashes here, the browns, and the little brown spikes are all clumped together at the bottom, and the ones are plotted at the top here. And we see the separation. The brown zeros are towards the left of balance, and the ones are towards the right. And the blue line is the linear regression line. And lo and behold, it goes below 0. So that's not a very good estimate of a probability. It also seems not to go high enough on the right-hand side, where it seems clear that there's a preponderance of yeses on the right-hand side. In the right-hand plot, we've got the fit of logistic regression, and it seems to do a pretty good job in this case. It never gets outside of 0 and 1, and it seems to go up high where it's meant to go up high. So it seems things aren't looking terrific for linear regression in terms of estimating probabilities. So now what happens if we have a 3-category variable? So here's a variable that measures the patient's condition at an emergency room. And it takes on 3 levels. So it's 1 if it's a stroke, 2 if it's a drug overdose, and 3 if it's an epileptic seizure. So if we code those as, say, 1, 2, and 3, which would be an arbitrary but natural choice, this coding might suggest an ordering, when in fact there's not necessarily an ordering here at all. And it might in fact imply that the difference between stroke and drug overdose which is 1 unit, is the same as the difference between drug overdose and epileptic seizure. So when you have more than 2 categories, assigning numbers to the categories just arbitrarily seems a little dangerous, and especially if you're going to use it in linear regression. And it turns out linear regression is not appropriate here. And for problems like this, we're going to prefer multi-class logistic regression or discriminant analysis, and both of those we will discuss.